Welcome to tangent and normal lines to parametric curves. So recall, in order to find a tangent line or a normal line, so in order to find the tangent line or a normal line to a curve at a point, the only information we need are dy dx and the point. The only information we need is the point and dy dx. From the previous video, okay, so from the previous video, we now have dy dx is equal to dy dt over dx dt, right, for a parametric curve. So in order to find a tangent line, so if we have a parametric curve defined by x equals f of t and y equals g of t, then the tangent line to the curve at time t equals t0 has slope dy dx equals, oops, sorry, I didn't actually finish. That should have been y equals g of t. The tangent line has slope g prime of t over f prime of t. Sorry, there should be t naughts at a specific point in time, and point f of t naught, comma g of t naught. So our line takes the form y minus g of t naught is equal to g prime of t naught over f prime of t naught times x minus f of t naught. And that's point slope form. We have our point, we have our slope. We can write the equation of our line. The normal line is the line that has perpendicular slope. So it's the line through f of t naught, g of t naught, which has perpendicular slope. So the slope, therefore, should be equal to -1 over dy dx, right? The opposite, or the negative reciprocal, otherwise known as negative f prime of t naught over g prime of t naught. So our normal line should have equation y minus g of t naught, the y value of our point, is equal to negative f prime of t naught over g prime of t naught times x minus f of t naught. So this is the formula for our normal line. Again, it's the equation of a line that goes through our point, which has slope perpendicular slope to the tangent line. So for example, let's find the tangent and normal lines to the parametric curve defined by x of t equals 3 cosine t plus 2 and y of t equals 2 sine of t minus 1 at t equals pi over 3. So note, we have, we can do our point first. So we have our point would be x of t naught, or in this case, x of pi over 3, comma, y of pi over 3, or 3 cosine of pi over 3 plus 2, comma, 2 sine of pi over 3 minus 1. Cosine of pi over 3 is 1/2. So we have 3/2 plus 2, comma, sine of pi over 3 is root 3 over 2. So we just have 2 times root 3 over 2, or root 3 minus 1. And so we wind up with 3.5, comma, root 3 minus 1 as our point. Then we can find our tangent slope. So dy dx is dy dt over dx dt. So dy dt is just 2 cosine of t dx dt, derivative of 3 cosine t plus 2 would be a negative 3 sine of t. So at t equals pi over 3, we have dy dx is 2 cosine of pi over 3 over negative 3 sine of pi over 3. And so this is 2 cosine pi over 3 is 2 times 1/2, otherwise known as 1. Sine of pi over 3 is root 3 over 2. So in our denominator, we have a negative 3 root 3 over 2. Or this is a negative 2 over 3 root 3. Otherwise known as negative 2 root 3 over 9. So this is our tangent slope. So our tangent line we have y minus, our y value was root 3 minus 1. So y minus in parentheses, root 3 minus 1 is equal to our slope, negative 2 root 3 over 9 times x minus, our x value of our point was 3.5. So here's our tangent line. Our normal slope is just negative 1 over 2 root 3 over 9. Sorry, a negative. We have negative 1 over negative 2 root 3 over 9. or a positive 9/2√3, otherwise known as 3√3/2. So our normal line we have y minus √3 minus 1 in parentheses is equal to 3√3/2 times x minus 3.5. Just a few quick notes. So note, as long as the curve is smooth, we can write a tangent line. So again, that's f dx dt and dy dt are not both 0. So as long as the curve is smooth, we can find an equation of a tangent line. If in the case that dx dt is equal to 0, then our tangent line would be x equals x of t naught. In the case that dy dt is equal to 0, then this is a horizontal tangent line. And we get y is equal to y of t naught. If the curve is not smooth, it may still be that there is a tangent line. So if the curve is not smooth, there may still be a tangent line. The trick for that is to find the slope. Try taking the limit as t goes to t naught of dy dx. Right. So, for example, if we have a sort of cusp to our graph where we're coming from a positive slope heading towards slope 0 from above, and a negative slope heading to slope 0 from above, positive slope heading to slope 0 from below, we have a corner, but at that point it still looks basically like it looks like the horizontal line. So at the corner, or at the cusp, we have that this looks like essentially y equals 0, right? A horizontal line. So just something to be aware of, even if we have this cusp, if the slopes happen to agree coming from both sides, we can still view it as having a sort of the slope existing when we have the 0/0 scenario. So if the curve is not smooth, again, if dy dt equals dx dt equals 0, dy dx would be a 0 over 0 situation. That's indeterminate. So we may still have sort of a slope, just looking at the limit. All right, so that is tangent line and normal lines to a parametric curve. In the next video, we will go ahead and look at the second derivative and concavity.